All right, so this is a lecture on Logistic Regression Lab. We have already looked at the data that we use for this lab. The data come from Selva et al. In the journal PLOS One. These authors assess the effects of distance to ungulate feeding sites on the probability of predation of quail eggs in nests. These quails lay eggs in the ground. So animals that might come over there because there is ungulate feeding site. Ungulates these are herbivores, and there might be other carnivores that might come there to feed on the ungulate. But while they are waiting there, they might look around and find these quail eggs, and they will eat those eggs. So that's the hypothesis, and they check that using this experiment essentially, where they put quail eggs at different distances from the ungulate feeding site and check whether that particular nest was preyed upon or not. If they were preyed upon, they scored that one. If they were not preyed upon, they scored that zero. So that's perhaps the first thing that you will need to do. If you analyze logistic regression type data, then you will need to code your response variable into ones and zeros. Okay, you might say preyed upon or not preyed upon in your data set, but eventually you will need to change those to ones and zeros. All right. So let's read in the data. First, we will load up the packages that we are going to use. You have seen all these packages before, so we'll start by loading tidyverse, dharma, performance, and car. And finally, we will load in the data. The data, I will call it nest. Okay, that's the name of the data. You can call it whatever you want, but something reasonable. All right, nest. So remember, the first thing to do after you reading the data is to check whether it actually looks okay. One of the ways to do that is by looking at its structure. And this tells us that it is a data frame. It has 240 rows and 7 variables. So that looks like that's what we need. The 7 variables are area, line, feeding, days, distance, nest type, and predation. In all of this, we are only interested in 3 columns: predation, distance, and days. Predation right here, that is your response, days, and distance. Those are your predictor variables. In particular, initially, we will look at distance. If the nests are far, then they are probably not going to be preyed upon, right? That's the hypothesis. So if distance does not have any effect on whether predation happens or not, then that means that ungulate feeding site does not affect the predation on the quail nests. Okay, so let's also look at this data in usual spreadsheet format. So area, line, feeding, days, distance, nest type, and predation. Note that predation is coded as an integer, ones and zeros. 1 means the nest was preyed upon. 0 means it was not preyed upon. And then there are nest types where they put them under log or in the bush or tree or something like that. And then the distance, and then days, how long after they check or something like that. So because Selva et al. Used log 10 of dist in their analysis, so that's what we will do. This should say distance, log 10 of distance. So that's what we will do also. So the first thing we do is log transform the column distance, and we will use log 10, and then we will save that as a new column in your data frame. Okay, so right now your data set does not only has 7 columns. Now you run this, and suddenly you see 8 variables, and you have log dist. Okay, all right. So let's plot these data. Remember, one of the first things that you do after looking at the data is whether there are any patterns, right? Exploratory data analysis. For now, we are only going to look at one. where we plot predation versus log dist. Log dist on the x-axis, predation on the y-axis, and we are expecting to see this lower sort of declining trend, right? When the distance is low on the left, there will be lots of predation. Predation actually happens. When the distance goes farther and farther, predation should not happen. So there should be more dots here, no or fewer dots on the top right, and then there should be no dots here, but it should decline, right? That's what we expect. So that's the model we are trying to fit. We are trying to fit a logistic regression curve that sort of looks like that on here. And to do that, we will use this function GLM from base R. This function is in base R, okay? And just like what we did in the plot, we put the Y on the left-hand side of that tilde. And then on the right-hand side, we put log dist. We provide the name of the data, and then we call it family equals binomial. Now, this is actually what is different for GLM compared to the model that we have been fitting so far. All the models that we have fit so far have assumed normal distribution or Gaussian distribution, right? Same thing, same name, just different names, but same thing. Now we are using binomial distribution because our response variable has two options, 1 or 0. Those are the only two options. Binomial, meaning two names, right? Two options. If there were 3 options or 4 options or more, then we would call that multinomial. There are also models where you might need them. But for now, we have to specify binomial. If we do not do that, R, I think, uses the normal distribution by default. Let's see, GLM, help base, it says family equals Gaussian, normal distribution by default. And in fact, if we change this, either got rid of it completely or change it to family equals Gaussian, the model will be exactly the same as the LM model that we have been fitting so far. So it would be the same thing. So we run this model and we will save that model as the object mod. Let's look at that. The base R diagnostics plots I have not found very useful for logistic regression models, so we will use the plots from package performance and ARMA. First, we will start with the package performance, and as before, we will use the function check_model. When we do that, we get a plot that looks like this. Okay, so this looks a little bit different from what you have seen before, but the ideas are pretty similar. The first plot, again, the green is the observed data, and the blue is the model predicted data, and the model predictions with the mean and the 95% confidence bands. That 95% confidence band should include that green dot. If your green dot is here and the blue lines are here, then it is not working. Your model is not very good. But now the blue and the green dots match pretty well, and the green dot is definitely included in the 95% confidence band, so that is good. Also note that the 95% confidence band is actually asymmetrical. What do we mean by that? Asymmetrical just means that the top part is shorter than the bottom part. And in the other case, the top part is longer than the bottom part. So they are not equal on the both sides. Normal distribution is one of those rare distributions where you have both sides being equal. Okay, T distribution is another one. But this distribution here for binomial, they are not going to be equal. But for now, just looking at the first plot, we would say that, yes, our model seems pretty okay. The second plot is about bin residuals, where the points should be within this gray error bound. And in our case, most of the points are within the error bounds, but there are definitely a few points that are outside. So yeah, maybe those are not represented very well. There are some data points that are not represented very well, and we will see what those are. The third plot shows influential observations. Remember, this is the same as we have seen before. The influential observation, there should be no points outside those green dashed lines. So not above or below that. In our case, all the lines are right within those gray bands. So those green bands, so we are good to go with that. There are no influential observations. And finally, the normality of residuals plot shows that the green line and the blue dots should match pretty well. And in our case, they actually do, except for some extreme values on the right. And I'm guessing that those extreme values are the same points that are problematic on the top right panel with the red dot and the line. So there might be some problems, but it's not looking too bad. It's looking pretty good. Another way to look at the model diagnostics is using the function simulate residuals from the package dharma. And to that, we only need to provide the fitted model object. And in our case, that is mod. That's the argument. That is the object that we provide to it. And we will save that as this object res, and then we plot that. Okay. So simulate the residuals first, and then we plot it. And the pattern that you see here, the outlook is the same, right? It has the same sort of design. Let's start with the one on the right-hand side. This plot is essentially looking at the homogeneity of variance assumption, essentially, if you will. And what we are supposed to see is that at different quantiles, this is the 50th percentile, 75th percentile, and 25th percentile. So everywhere it should be pretty flat. Okay, and in our case, it is curved a little bit, but this curve is actually not significantly problematic. This package actually runs some statistical analysis also and checks that not only visually, but also using statistical tests. And what this package has said is that there are no significant problems detected. So we are good to go with the homogeneity of variance assumption. Then we look at the normality assumption using the KS test on the left. The p-value is 0.88, which is much higher than 0.05. So the normality assumption is met pretty well. Dispersion assumption is met pretty well also. And the outlier test also shows that there are no influential observations. There are no outliers. So our model assumptions seem to have been met pretty well. Now, all of this, you might realize, do not actually test the linearity assumption. That is one of the key assumptions of any linear models. And GLM is still a linear model. It is a generalized linear model, but it is still linear. So how do we check whether there is a linear, whether there is linearity? To check that, we plot log dist on the x-axis and predation on the y-axis, just like we have done before in the model. And then we will put a smoother across it so that we can see whether there is a pattern. We will add the lowest smoother. You remember lowest smoother is just sort of, instead of picking just one straight line, it just tries to look at the flow of the data, right? Locally estimated scatter plot smoothing. That's what that stands for. Okay, so when we look at that, we see that indeed when log dist increases, the probability, the probability of predation decreases. So that's good. But at the very end, it actually goes up a little bit again. This last part on the very right is not what we want. This is against our assumption. But for the most part, yes, there is linearity, and that is good. That's what we wanted to see. So the linearity assumption seems to be met, but there are some problems. We can also essentially create this plot using one line in base R, and for that we use scatter.smooth function, which is what we have seen before in multiple linear regression. So we can create it like this. And this does not give you the 95% confidence band, but the line is pretty much exactly the same. And we wanted to see a linear pattern, but there is an upward trend at the very right. Okay, So we will proceed as if all assumptions are met. There are some problems we know, but this is what we have right now. And if we wanted to make sure that we capture this difference at the very right also, then we would need to use a more complicated model, just like a smoother, including a smooth function essentially. So let's look at whether how good our model is. The first thing we will look at is what is called the goodness of fit test. And to do that, we will use the function ANOVA from the package car. When we look at that, it provides us the analysis of deviance table, not analysis of variance. Analysis of variance is what we had used for linear models. Now we are general linear models. Now we are using these for generalized linear models, and generalized linear models do not have analysis of variance. In fact, what they have is analysis of deviance. But you can interpret it in much the same way. And the test statistic is the likelihood ratio chi-square statistic. This is different from what analysis of variance did. Analysis of variance uses the F distribution. Analysis of deviance uses the likelihood ratio chi-square distribution. Okay, it uses a whole different distribution. Also remember that analysis of variance has 2 degrees of freedom, right? F distribution has 2 different types of degrees of freedom: numerator degrees of freedom and denominator degrees of freedom. But chi-square distributions only have 1 degrees of freedom, and in our case, that happens to be 1. This essentially is because we only have one predictor variable. Okay, for 1 degrees of freedom and chi-square of 27.21, which is pretty large, we get the p-value that is really, really small. Now, how do you interpret this? This model is essentially checking, this test is essentially checking whether this model, our model, is better than the null model. Remember that the null model is one where we do not have any predictor. For example, if we got rid of log this and replace that with 1 means intercept, then that is a null model. It just means that just take the average and there's no difference, right? No predictors are important. It's the same as just taking the average. But we are comparing our log this model with a model without any predictor variable. And we find that, yes, they are significantly different, meaning that our model is considerably better, statistically better than the null model. So yes, the predictor variable is important. Is the predictor variable important? Useful? Yes, it is useful. Then the question is how useful, right? How useful? We look at the summary output first. And in the summary output, it gives you quite a bit of information. Some of this is perhaps not necessary. It gives you the null deviance, residual deviance, it gives AIC values, it gives you the number of iterations it took for the model to fit. Then it also gives you the parameter estimates and their p-values, and that is what we are interested in. We are interested in knowing about the parameter estimate and whether the parameter estimates are different from 0. In particular, I am interested in looking at this second one, which, remember, is just the slope, right? This is just the slope. The slope is negative, and is it different from 0? Yes, it is different from 0 because the p-value is much lower than 0.05. This tells us that log this, the slope, this line, for example, instead of having a straight line, our line has some slope, and this slope is different from 0. There is actually an increase or decrease, but it is significantly different from 0. It is not flat. Okay, it is not flat. Just like before, when we were comparing general linear models with ANCOVA or linear regression, we looked at whether the slope was different. That is what this is checking also. Okay. So we can access these estimates directly by using the function coef, which we do in the next line. So this gives us 1.733, and the slope, which is these values are the same as we saw before. But remember, for interpretation, it is often easier to actually look at, these are the log R's, right? These are the log R's. It is often better to look at R's. To look at R's, we would exponentiate the coefficients, which is what we do here. And if we just run that, this gives us these really big values. Big meaning there are lots of decimal points. We don't need that. So I round that to the nearest 2 digits. And when we look at that, we get 5.68 and 0.45. And how do we interpret that? Most importantly is the slope part, the odds part. So let's interpret that. This means that just as in linear regression, when log dist increases by 1 unit, when log dist increases by 1 unit, the odds of predation, right, because this is looking at odds, the odds of predation increases by 45%. 0.45 is 45%. So the odds increases by 45%, but what does that mean? That actually means that the probability itself decreases because it is less than 1. More than R's more than 1 would mean that with the X variable increasing, Y also increases. But because the R's is less than 1, the probability actually declines, which we can see from the plot on the right also. The plot on the right shows that when log dist increases, the probability of predation actually declines. And now we know it declines by about 45% in terms of odds. Then we look at how good the model is. Remember, we can essentially check that by fitting a null model, which, as I said before, is the model that has only one, the intercept on the y, on the x, so on the right-hand side. So we will fit this model and we'll call that null mod. Now, to get the R-squared value for our model, we can essentially compare the likelihood of our model versus the log likelihood of the null model and subtract that from 1. When we do that, we get R-squared value of 0.082. That is the R-squared value. Forget about all this other stuff that it outputs. But the R-squared value is 0.08, meaning that 8% of the variation in the data are explained by the model. That's not very good. That's not very good at all, right? It is not very good. But we know that McFadden's R-squared, which is what we are calculating here, is usually too low anyway. So R-squared values in general for generalized linear models are not very, very good to look at. We do not have very good metrics, simple metrics like that. The function model underscore performance from the package performance also gives us another type of R-squared called Tuor's R-squared, which in this case is 0.112. Tuor's R-squared is 0.112. Now, this says that 11% of the variance is explained by the model. Again, Tuor's R-squared is also biased low oftentimes, so usually not very interesting. And all these values about AIC, AICC, and PIC, those are not very informative for us right now because they are only useful when we are comparing 2 or more models. Right now, we are only comparing 1 model. But we can do this, right? We can do mod, and we can compare that with null mod. If we do that, actually, apparently it is not supported. Huh. Okay. All right. So the next step is we will look at actually creating our final plot and checking what the probability of predation is at particular values. To do that, we first create a new data frame called new data 1. So we make that a data frame. For that, we need to provide the column log dist. And for that, we provide values from the minimum of log dist to maximum of log dist, and we want 100 values between the minimum and the maximum. That's what this is saying. Okay, so let's create this, and then we can look at it a little bit more. So we create new data. If we look at new data, it has one column. The lowest value is 0.954. Let's look at our actual data. Yes. Lowest, the lowest is 0.954. That's what we have. We started with that. And the highest is 3.576. So that's what we should have here also, 3.576. And between that, we create 100 values. Why 100? Yeah, we could do 50 if you want, or 500, whichever, it doesn't matter. But 100 is pretty good because that will give us lots of data points where we make predictions and it will give us a smooth line. Suppose we did 10. Let's just start with 10. Okay, 10 values. Now we will have 10 values here between 0.95 and 3.57. Then, because this is all in log dist, we want to convert that to distance so that it is easier for us to understand the data. So we will create that new column called distance by 10 to the power log dist. Earlier, we used log 10. That's why we are doing 10 to the power. Before, in some other exercises, we were doing natural log. That is why we are doing exp, right? Exponent. But because now we are using log 10, we will use 10 to the power. So we do that, and now our new data has a second column, 0.95, meaning 9 meters away, and 3.57, meaning 3770 meters away. So long distance away, right? Almost 4 kilometers away from the ungraded feeding site. So we have lots of values. Now, for all of those values, we make predictions at the log R's. Okay, so we use the function predict. For it, we provide the model object mod, and then we say make predictions at new data one. New data is the name of the argument. New data one is the name of our data frame. And then we say make predictions at the link scale. Remember, the link for binomial distribution, the logistic regression, is logit link. So we are making predictions at logit link, and then we say also give me the standard errors. Okay, give me the standard error also at the logit link. All right. So when we do that, it should create a new object called fitted. If we look at fitted, um, let's do. You can just probably do it from here. Fitted has three things. Fitted has 10 values for the main prediction, and then its standard error. Might be easier to look at new data one. Actually, let's do this. cbind and the new data one and fitted. We are combining the new data and the fitted together. And this is what it looks like. So log distance, this comes from new data, and fitted has three things: fit and SE fit and the residual scale. Forget about residual scale for now. But fit is this is the logit, predicted logit, okay? And SE fit is the predicted SE for the logit. This is all done at the link scale, okay? So this is the logit or the log R's. The log R's of predation occurring at 9 meters. This is the log R's of predation happening at 17 meters. This is the log R's of predation happening at 3770 meters. Okay, so then we will, because this is all R's, we want to convert that to log R's, we need to convert that to R's. And how do we do that? We convert log R's to R's by using exponent. Okay, exponent, and we make that R's. So we create a new column called R's, odds, let's just run this much. I just added a parenthesis there just so that I can see what is happening. Okay, so a new column called odds. So for the same distance, the odds is 2.63, and the odds at the very end is 0.32. Remember that odds more than 1, so anything above 131 meters, I guess, anything above this means that probability of predation happening is more than 50%. There's a pretty high chance of predation happening, more than 50-50, right? More chance of predation occurring than not occurring. And below that, the probability of predation occurring is less than the probability of predation not occurring. So the predation is not as likely. And as the distance increases, it becomes less and less and less likely. Predation becomes less likely as we go from top to bottom. Okay? All right. Now let's get rid of that. Then we will also convert the odds and such to actual probability. Because we used the logistic regression with the basic, the default link, which is logit link, we can reconvert it back to probability by using this function plogis. Okay, this converts the log odds to probability of predation. So we can do that here. Let's just run this much now. Okay, so we have one more. And as I said before, the probability of predation occurring is very high when it is just a couple of meters away. And as the distance increases, the probability of predation occurring declines over distance, right? Okay. Then we can also get the 95% confidence bands for these probabilities by, again, first we will subtract the 1.96 times the standard error of the fit. So this gives us the lower confidence band, and this gives us the upper confidence band. But both of these happen at the link scale. Now we need to convert that to probability by, again, using plogis. So now let's run all of this, and then we will see what it gives us. Let's look at the head of the data frame. Let's run it again. So now we have the different distances, log distances, and then the R's at each distance, probability, the 95% upper and confidence limits for each of those also. Then we can plot it. To plot it, first we will start with the new data. On the x-axis, we'll put distance. On the y-axis, we'll put probability, which is prob. And then at the very bottom of that plot, I will add the ribbon for the 95% confidence band. For that, the y minimum, the band should have a minimum and the maximum in the y, right? So that would be the minimum is lower limit, maximum is upper limit, and then I make it sort of translucent by using alpha equals 0.3. Let's run this, and it creates a plot that looks like that. Okay, don't worry about the shape right now. Just note that there is the 95% confidence band. Now we want to add the actual line, actual prediction. So we do that by adding geom_line. So we have our actual prediction there also. And then we finally add the data. And for that, we need to use the data frame nest. On the x-axis, we have distance. On the y-axis, we put predation. And we jitter it a little bit. Not on the width scale, not on the distance scale, just up and down a little bit. So we create that and we save that as the object P1. And that's what our data look like. Okay, so the black dots are our raw data, and there's the 95% confidence band and the actual probability of predation happening at each of those places, each of those distances. Notice, first of all, how jagged those lines are. You see how there are like one point right there, and then straight, and then straight and straight. It is not really smooth, right? Why is it not smooth? I think you can guess it. So look at these values, right? there are 10 of those corners because we looked at 10 values. If we had done, let's say 20, it would be less jagged. Okay, let me run through all of this. Yeah, this is smoother, right? But you can still see a little bit of those angles. To make it even smoother, we can increase it by, let's just make it 100. And now things will look pretty smooth. Of course, you can make it 1000, and that's fine too. That will make it really smooth, but that's an overkill, right? It doesn't really look much different, does it? The line itself, no, it doesn't look very different. So that's why I used 100. Okay. All right. So here we go. We have a plot, but it does not look like the logistic regression plot at all. Logistic regression is supposed to have this either S shape or the upside down S shape, and we do not have that. Why is that? Well, that's because we are plotting distance here. If we had done log dist everywhere, log dist here and log dist here, that would have been okay. That's what we wanted, right? Sort of like an S shape. But this is log dist. We want to, log dist doesn't make sense to a lot of people, right? So we would want to make it distance. By the way, just so you know how to interpret log, especially log 10 values, 1 corresponds to 10. 10 to the power 1 is 10. 10 to the power 2, that's what that is. That is 100. That is 100 meters. 10 to the power 3 right there, that is 1000 meters. Okay, just so you know. All right, now let's go back and make this distance because that makes more sense. We'll create this plot again just so we can see that. And now to actually have it go from, make it a better scale, we can use something called scale x log 10. The x scale, the x-axis, will scale that by log 10. This is a default function. This is a function that is available automatically in ggplot2. And when we do this, we see that the distance now goes from 10 to 100 to 1000, just like we just saw before. And the curve looks right. This is exactly what we wanted. And as before, you can see that when the distance is low, say 10 meters or less than that, the chance of predation happening is more than predation not happening. This is the above this black line is the chance of predation happening. And this is not happening, right? It is more likely to happen than not likely. 50-50 is right there. Here at the other end, though, predation is not likely to happen compared to the chance of predation happening. Wouldn't it be good to actually predict where it is 50-50? This is a very interesting question oftentimes, especially if you work with ecotoxicology data, where you want to know what is the concentration where 50% of the individuals die, or something like that. Or perhaps you are looking at maturity data and you say, what is the age or length or height or whatever when 50% of the individuals are mature, right? If you have to give a particular value to the whole population, at what age do they reach puberty? You can say, yeah, 13 to 17, but what if you have to give just one value, what would that be? Where is 50-50 chance? We want to get that value right there. To do that, we can use this function dose.p from the package mass. That's why I did that. Okay, that's why I do that. From the package mass, use the function dose.p, which will give you the log dist at 50% chance of nest predation happening. Log dist, 5.16 is the log dist. Now we need to convert that to actual distance. To do that, we do 10 to the power, right? So it is 145. Does that look right? 145, so 50% chance here. And we come over here, so 100, a little bit over 100. So yeah, 145 meters is where the probability of predation is 50-50. You can also get the 95% confidence band, which you can probably get from just looking at this also. But how would you get that? There are ways to do that, not the most straightforward, but you can figure it out, and it will be in your homework assignment also. Now, the rest you're supposed to do at home, but because this is a recorded lecture, I will explain this also. The question now is, well, all of this only use distance as the only predictor. What if we have more than one predictors? Suppose we have days as another predictor. And if we want to do that, in our case, days, let's look at our data. Days, how many options do we have? 6, 6, 6, 15, 15. Oh, yeah, there are not a lot of values, right? Even though it is a number, it is probably better to use that as a categorical variable because there are not a lot of options. So we first convert that into the factor, and then we save that. Then, just as before with multiple linear regression or ANCOVA or something like that, we just add that second variable right into the GLM model on the right-hand side. So before we only had logdist, now we have days also, days plus logdist, or you can do logdist plus days, doesn't matter. Everything else is the same. So mod 1, car. So now you get two columns, two rows, right? Days and logdist. Clearly, days is also an important predictor variable because the p-value is less than 0.05. So days also affects whether predation occurs or not. Then you can look at the summary statement and how would you interpret this. We will look at days 15 now, right? So this is for day 6. This is for day, this is the difference from day 6 compared to day 15. So to actually get the value for day 15, you would need to add 1.45 plus 0.658. Okay, and 15 and 6 days, those two values are significantly different from each other. That's what this p-value is saying. Now, to plot your data, you would need to essentially get the values for both. Get the values for logdist for as before we have done, but also get that for each of those days, for 6 days and for 12 days. So first you convert that to you create a new object called days. Let's just see what that gives us. Okay, that is just two values, 6 and 15. And let's do 100 here. This is exactly the same as before. So you have two columns, right? Two vectors, if you will. And then we expand underscore grid. What that means is, I think it is probably easiest just to show you what those data look like. So for 6 days, it will create those 100 values. And then it is again repeated for 15 days. Each combination is shown. That's what expand underscore grid does. It provides combinations for each of those vectors. So we have 200 rows now instead of 100 rows. And then, as before, we will do the 10 to the power to get actual distance. The rest is the same as before. I just copied and pasted the code. When you look at this, you find that the coefficient, days 15 has higher probability of mispredation. Days 6 has lower probability of mispredation compared to each other, right? And then we also show the points, different shapes and colors, different colors based on the different days. And we do that just by adding fill equals days for ribbon, call equals days inside aesthetics for line, and then also call equals days in the geometry, right? So just as before. Okay. And I also cleaned up the X and Y axis limits a little. We can also get the distance at 50% probability of mispredation for different days. These are our coefficients. We can do 10 to the power and then dose P. And what is this doing? What is all this 1 and 3 business? Okay, So for day 6, we start out with, this is for day 6, remember, and then this is for the log dist, right? So the first one and the third one, that's for day 6. For day 15, we have used this one, right? The second value, and that is why we get that. Actually, it should be, that's not quite right, is it? Let's see. 10 to the power, this is for day 15. Day 15 is in green, 50% chance. Yeah, that's not quite right because this value should not just be 1 and then 45, but rather it should be 1.45 plus 0.658. So that doesn't quite work. But you can calculate, figure it out how you can calculate that. All right, this is all we have for today. If you have questions, please come find me. Thanks.